All right, any questions before we get back into the stuff? Okay. So we ended last time talking about this idea of diagonalization. So if I give you a square matrix, in some cases it can be broken down into a few different matrices, the product of a few different matrices, one of which is purely diagonal. So what were those criteria? What conditions do I have to meet for a matrix to be diagonalizable? For which, so for at least one eigenvalue, how many eigenvalues does that have to hold for? Every single one of them. So I think this one we did yesterday, if we would have started with lambda equals 0, we could have been done a lot earlier, because this one is the one that told us that we couldn't diagonalize this matrix. Because what was the multiplicity of 0? It was 2, or the algebraic multiplicity. And what's the geometric multiplicity? How do you know? What does that phrase even mean? Ooh, I heard a lot of mumbles. There's only one vector in the basis. So those two things have to be in lockstep, every single eigenvalue, or else we can't diagonalize. So let's diagonalize this one if we can. So how do we start that process? What do we have to do first? Find what? Find the lambdas. So I'm going to make our characteristic matrix. How do I find the determinant of this thing? Got to expand it. We got some choices. How would you like to expand it? Row 1, how come? There's 2 zeros up there to take advantage of. So we're expand by minors off of row 1. How many minors do we have to make? Just the one. Just 1, 1, which will be 4 minus lambda, negative 1 minus 4, 4 minus lambda. That determinant will be 4 minus lambda squared minus 4. Okay, are we good so far? Okay, so now that I have this determinant, what else? Okay, what's the cofactor going to be? 2 minus lambda. So yeah, I'm going to multiply it by the entry that I kind of centered that expansion around. So now I have 2 minus lambda times this 4 minus lambda squared minus 4. That all equals 0. One more thing to worry about. Do I need to multiply this by negative 1, or am I okay? Okay. Because negative 1 to the 1 plus 1. Even power. All right, so what are my eigenvalues? One of them is 2. So I have 2 minus lambda equals 0, so I get lambda equals 2. The other one's going to come from this. 4 minus lambda squared minus 4 equals 0. So 4 minus lambda squared equals 4. got some options here. You want to expand that or do something else? I'm going to square root. If I square root, then I get 4 minus lambda equals plus or minus 2. Minus lambda equals minus 4 plus or minus 2. So all that work to give me lambda equals what? 6 and 2? Right, so I think I have two distinct eigenvalues. One is 2, which has a multiplicity of 2. And the other one is 6, has a multiplicity of 1. Good so far? Okay. Should we keep going? Or are we stuck? We don't know if we're stuck yet. So where do we go from here? Okay. Let's do that. So if we say lambda equals 2, then the matrix I want to deal with is 0, 0, 0, 1, 2, -1, -2, -4, 2. Anything jump out at you? There's a row of 0, so we're gonna have at least one parameter if we can reduce this. What else? Or right. So the third row is the opposite of the double of row 2, which means this is really what I have. So the only row I have is that, so what's left? What does x1, x2, and x3 equal? Actually, let's go slower. -2x2 plus x3. So how many parameters does this imply? 2. Is that a good sign for us so far? Okay. So we expected to a basis with 2 vectors in it. So then let's write this out. So x1, x2, x3. Okay, so maybe this is still diagonalizable. So now what should we do? Okay. See if I can buy myself some room. There. That was gross. That's okay. Whoa. All right, now when lambda equals 6, then the matrix I get is -4, 0, 0, 1, -2, -1, -2, -4, -2. What can be done with this? First row, yeah. Scale that down. So I got a pivot. What can I do with that pivot? If I have a pivot, if I have 1, 0, 0 in the top row, then that means I can zero out that column, right? And now row 3 is I can multiply row 2, so get rid of row 3. Right. So row 2 and row 3 are not identical, but multiples of each other, which means I can do this. And I like looking at positive numbers better, so I can do that. All right. So what did we just learn? X1 is 0. Let's try to avoid fractions. So x3 equals negative 2x2. All right. So how many parameters does that imply that we need? I just see x2 on the right-hand side of the equal sign. So what does that say about diagonalizability? Can we definitely do it, or do we have to still look for stuff? Look for clues. Actually, if we can diagonalize, that will be true. So, but based on what we've done, so I think we've looked at all the eigenvalues, right? Have both eigenvalues met the criteria that we care about? So then A will equal PD P inverse, as long as we call PDP inverse the right thing. I believe that's what that vector should be. I agree with you. Thank you. I told you that reversal was common. No one's immune to it. Okay, so hopefully we have all three eigenvalues. We know what eigenvectors go with each one. We know that the multiplicities line up in a way that diagonalization requires. So now how do we do it? Yep. So I'm going to make a new slide because I don't want to try to force that. So now that we know this can happen, so this thing equals PDP inverse. And we have some guidelines about how to construct these things. What does P equal to? Really, we just have to find P and D. Which one do we want to define first? Okay, what's P equal to? So is there any specific order you have to put the eigenvalues in? No. Okay, so negative 2, 1, 0. Negative 2, 1, 0. 1, 0, 1. 1, 0, 1. 0, 1, negative 2. 0, 1, negative 2. So there is no specific order in which you have to build P or D, but now that you have constructed P, D has to follow suit. So these three column vectors you gave me, what eigenvalues do they go with? 2, 2, 6. Okay. So then this diagonal matrix needs to be consistent with that ordering. So what's this matrix need to look like then? And then P inverse is the thing that you can find, where you can ask the calculator to find for you. Another guarantee for this process is that P, if you construct it the right way, is guaranteed to have an inverse. So when we say that A is diagonalizable, that means that all the things you need to make this diagonalization are going to be well defined. They're going to exist. So someone shout out P inverse at me whenever.
I got negative 1/4.
Negative 1/4?
1/2.
Am I going rows or columns? Okay. 1/2. 1/4.
And 1/2. 1/2 again. Then 1/4. 1/2. And negative.
Okay. And then if you're feeling like you want to complete this, you can make sure that that product gives you A. But I believe we did everything right, so that should check out. How are we doing with this process? And are we understanding how to know when you can give up on it? So I think the last thing we did last time was I gave you one that we gave up on, right? Okay. Any questions? Go ahead.
We're done after we find PDPs.
Yeah, so that's basically diagonalization. What we're really doing is we're decomposing A into a product of these three things. So once you find those other three matrices of the same order, you're done. It might feel a little bit weird to leave them as like this unevaluated product, but something we'll do after the test is we'll talk about a few different ways to decompose matrices. There are a few useful ways to break a matrix into more digestible pieces. Like, for example, like any matrix can be broken into two pieces, one of which is upper triangular, the other piece is lower triangular. Those are separately easier to analyze than the thing they come from. All right. Got one more thing for you. And then if we have some time to review, we'll do that. I think we will. So let's do some things with this diagonalizability idea. How do we find A squared? I can multiply A by A, right? So just write them side by side. That's not too hard to do by hand, right? What order matrix should this product be? Also 2 by 2. And what's this product going to look like?
$36, $36, 1/4.
36, 36. And what?
1/4. Like 1.
I think so that looks to me like you're multiplying like the corresponding elements.
Oh, right.
That is not how we do multiplication. So yeah, let's refresh that. So if I want to find what goes in the first row, first column, how do I get there?
2, 6 minus 6 plus -6.
Right. So basically you're doing this dot product idea. So if I want to get row 1, column 1 of this matrix, I multiply row 1 of this matrix by column 1 of the second matrix. So 6 times 6 plus -6 times -1. And then we'll basically use the corresponding rows and columns to do the rest of this. So row 1, column 2 should be -36 minus 42 minus 78. And then -6 minus 7. minus 13. And then 6 plus 49. Does it look okay? -42, -13, -78, 55. Okay, we okay with that? All right, so that's from a while ago. Why did I ask you to do that? What about 8 to the 10th? How would we do that? Especially, what if I asked you to do it by hand, which I'm going to? I believe strongly you could do it. But if I'm asking you to do it by hand, there's probably a better way. What if I promised you that A could be diagonalized? If A can be diagonalized, then how do we write it? Or how can it be written? PD, P inverse. I haven't found these things yet, but I'm promising you they exist. If A is equal to this, then what does A squared look like? Isn't it also PDP inverse squared? Which is PDP inverse, PDP inverse. If I lay out those 6 matrices like that, do you notice anything? These become the identity. So what I'm left with is P is this, right? Or I could just say PD squared, P inverse. Does that make sense that I'm allowed to do that? What if I were to lay 10 of those out side by side by side? Let's make sure that, I mean, I'm not going to count all the way up to.
Or like do a square layout square.
Oh yeah. Right. So I could call A to the 10th, A squared to the 5th, and I could lay out these. But also let's look at A to the 3rd here. All these inner P inverse and P are going to cancel each other out, right? So this is going to become P times some power of the diagonal matrix times P inverse.
So then I assume like they did the
Absolutely. So this is one of the things that this diagonal decomposition is good for, is that you can evaluate A to any power, including the case where I want to keep that power arbitrary. So A to the K is equal to P D to the K, P inverse. How are we doing? We okay with the rationale and why that works? Okay, so now let's do that here. But we have to find those matrices, right? So how do I diagonalize A? Find the eigenvalues. Where do those come from? A minus lambda I, which is 6 minus lambda minus 6 minus 1, 7 minus lambda. Take the determinant of this thing. Minus 6 equals 0. Lambda squared minus 13 lambda. plus 36. Someone double check me. Okay. All right. Does this factor? Should factor into lambda minus 4. Lambda minus 9 equals 0. Lambda equals 4 and 9. All right, now what? Okay. Okay. So A minus 4I equals 2, negative 6, negative 1, 3. What do we do with that? When we reduce it, what do we get? So I basically, one of the rows I can turn into zeros. So I know I've been doing that kind of quickly in the last few examples. Why am I allowed to do that? What's that? Yeah, right. One is precisely a multiple of the other. And from the elementary row operations we know we're allowed to do, that means I could add whatever the correct multiple is to that row, and I could annihilate it. So now from this, what do we know about x1 and x2? X1 equals 3x2. So a good eigenvector would be what? 3, 1's a good one. All right, so let's look at A minus 9I. Negative 3, negative 6, negative 1, negative 2. Are these rows multiples of each other? Okay. And with a 2 by 2 matrix, if that doesn't happen, then there's a mistake. Because the whole point of eigenvalues is to get this new matrix that has dependence. So when you only have 2 rows, the only way they can be dependent is for one to be a multiple of the other. All right, so what have we learned here? X1 equals negative 2x2, which means I have, give me a good vector here. Negative 2, 1. So do we have all the right pieces to diagonalize this now? Okay. So now I have that A to the 10th equals P, which is what? Yep, those two columns. So 3, 1, negative 2, 1. If that's what you said P looks like, then what does the matrix D have to look like? 4, 0, 0, 9. That raised to the 10th times the inverse of I think that's the inverse. Okay. So we really given ourselves anything easier to do, we're still having to multiply a matrix by itself 10 times. What's that? I'm not letting you use a calculator for this though, because it doesn't build character in the way that I want to build character. So yeah, that's exactly that's what we bought ourselves. So let's just do real quick 4009 times 4009. What would that look like? 16 plus 0, right? And then the next one would be 4 times 0 plus 0 times 9. And then 0 times 4 plus 9 times 0. And then 0 times 0 plus 9 times 9. So when you multiply two diagonal matrices together, you're basically just multiplying the corresponding elements together. Everything else is going to fall off. So that is the shortcut that we get for free. Okay, touche. Then don't. This is not incorrect. 4 to the 10th is a number. So is 9 to the 10th. If some of you are computer science majors, you might know what 4 to the 10th is, but don't worry about it. It's that weird 1,076,000 something like that. But is this a multiplication you can do? Yeah. Cool. Any questions about how we did this? All right. Let's kind of go the opposite way. Can we find a matrix like essentially a square root matrix? So one thing we've guaranteed, and we already now we've seen the pieces. Now here's essentially what I'm asking about. Is there a matrix I can multiply by itself? To get A. How do you take a square root of a matrix, though? You believe we can? So here's what you're saying. P d to the inverse. So here's what our individual or our specific matrix looks like, right? It was 4009. So even though square rooting a matrix is not something that exists, technically, what would you call this? I mean, it's not like I contrived the factors 4 and 9 for this specific purpose. But let's do, so we're not making any alterations to that matrix P, right? So what happens if I square S? Well, same thing as before. These inner inverses and are going to cancel out with their matrices. What is d to the 1/2 times d to the 1/2? Yeah, that is exactly what you would do. Are there others though? Are there other matrices that would work like this? I think there are 3 others. Because basically what you did is this. Why did you give me the numbers 2 and 3? Where did they come from? Square root of 4 and 9. So there are numbers that if you were to square them, they would become 4 and 9, right? Are there other numbers that do that? Really, any of these are going to work. So that's why I'm saying there are 4 matrices that do this, because there are 4 different combinations there if you flip the signs on both 2 and 3. So S can look like this. P d to the 1/2, or like any of these things. P inverse. Where, and to be really clear, the matrix I'm calling P here is identical to the one we just got done constructing. How are we doing? Okay, let's do one in general and then we'll be done. I want to find a general formula for this matrix raised to any power at all. Which means I'm kind of taking something for granted. What do I have to be taking for granted? I have to be able to do that. Otherwise we can't. There's no real way to generalize this aside from diagonalizing it. So how do we start doing that? Okay. And this is too big. This is bigger than 2 by 2. So how do we find eigenvalues for this thing? Yeah. So we're going to put in these new entries along the diagonal. We're going to find the determinant by expanding by minors. How would you like to expand? Column 1 is probably the easiest choice.
Wait, why not? Actually, why not?
Row 3, I think, would be equally. Yeah, so what was that? Oh yeah, on row 3 you're gonna have, so in row 3 you have 0, -1, and then negative lambda.
Oh, yeah.
Yeah, if you're gonna find the determinant of that matrix as is, then row 3 and column 1 are both equally good. All right, so if we expand on column 1, how many minors do we need? Just the one, the first one. Three minus lambda to -1, negative lambda. What's that determinant? I'm not going to expand that yet. All right, from there, what do we have to do? Multiply by the cofactor, which will be 2 minus lambda. And that's it, right? Okay. Do a little bit of rewriting. that factor again? I think it does. Yeah. 2 minus lambda minus 1, lambda minus 2. So what are my eigenvalues then? Yep. All right. So now that I have the eigenvalues, what should I do with those? All right. So a minus I becomes 1, 4, 8, 0, 2, 2, 0, -1, -1, which is the thing that one of you will reduce. Yep, I can see that now.
Yeah,
1, 0, 4, 0, 1, 1. All right. So then what are our eigenvectors? Yeah, what does this tell us? X1 equals -4x3. X2 equals -x3. So that's how many parameters? Just one. Which is the number of parameters I wanted. All right, then what about a minus 2i? Zero, 4, 8, 0, 1, 2, 0, -1, -2. I think I can see how that's going to reduce. All three of those look like the same row, right? Okay. All right, so what does that tell us? It tells us that x2 equals -2x3. What does this mean by x1 though? Oh, I think x1 is just totally free, right? Okay. So that, okay, I was trying to figure out how we're going to get a second parameter out of this. This does not say that x1 has to be 0. Just x1 is totally untethered. Okay. So then x1, x2, x3 equals x1 times a vector plus x3 times a different vector. I think x1 is just 1, 0, 0. And then x3 will be 0, -2, 1. All right. So now we should be able to do the thing we were asked for. What is a to the n? Well, it should be equal to p times d to the n times p inverse. So what's p? It should be made of things that I've already written down, right? What order should I write them down in? -4, -1, 1, 1, 0, 0, 0, -2, 1. And by doing that, you have forced the order of this next matrix. 1, 0. So, and remember, I'm going to raise all these to the n, right? Except that doesn't do anything to 1. So 1, 2 to the n, 2 to the n. And then times the inverse that someone's going to find. Awesome. Got it. Any questions about any of this stuff? Or are we we feel like experts? Ready for Monday? So I have 148. I'll give you all a choice here. What I was planning to do, I was just going to open up one of the practice tests and kind of run through it. Or I could just call this office hours. You can toss me whatever you want. What are you feeling? Have you all had a chance to look at the practice test yet? Okay. What do you feel like doing? Let's do it. Okay, so I'm just going to shuffle. So this, like, you tell me what you. That's not it. I thought that I opened it. I did. 24 pages of stuff. Um. Oh, is that it? Oh, okay. So given a matrix, find a basis for null row and column space. Find the rank and nullity. And you're even given the reduced row echelon form. How do you feel about that? Should we talk about it, or better things to talk about?
For row space and column space, we take our rows and columns from A, not use version, right?
For the column space, you take it from A. I mean, you can do either. On Infinity, I am a human though, and I am more thoughtful. But like in reality, a good basis for the row space here is the top 3 rows of R. It's also the top 3 rows of A. So I mean, I will take a look at it. So they kind of walk through how to find these things. So the basis that I'm guessing the coordinator wrote here is from R. The column space is from A. How to get from one basis to another. What is this? Given a bunch of vectors, is this vector in the span of it? So we've done stuff like that. But I still recommend that, I recommend at least looking at this on your own. A lot of things in math have a way of seeming much easier when you're in a room with your instructor and a bunch of other people learning it. Make sure that this makes sense on your own as well. Find a basis for this subspace and find the dimension of that. So I'm kind of just reading through this. If anybody wants to stop and go through one in detail, we can. Or if it's just kind of comforting to kind of know what you should be getting ready for, I'm good with that too.
I have a question. I guess yesterday.
Yeah.
So it asked us about the trace of the system.
Yep.
Should we expect something like that on the test?
No, then there are certain things I'm okay with asking you in a forum where I know you can Google things. So the trace is, I don't think I've ever brought it up in here, but it's a very easy thing to calculate if you know what the heck it is. Which is why I left that question in.
Okay.
What is trace?
That's just
Yeah, so yep. Anything in particular you want to talk about, or are you feeling confident about Monday, or right now is it too early to ask you about what you need? Okay, let's do this. Let's shut down a little bit early. I don't want to get into new stuff right now and muddy the waters.